In this video, we're going to talk about Stork enamine synthesis. This is very closely related to the Michael reactions that we saw in the last video. As we talked about in the last video on Michael reactions, regular enolates don't give Michael additions. They're too reactive, so we get 1,2 addition rather than the 1,4 addition that we want in a Michael addition. So a chemist named Gilbert Stork developed a synthesis using an enamine as an intermediate to allow us to do Michael reactions with regular enolates. And so a couple chapters ago, we learned how to make an enamine. If we react that with an acid catalyst and a secondary amine, we can convert our ketone or our aldehyde into an enamine, where we end up with a carbon-carbon double bond next to the new carbon-nitrogen bond that we formed, replacing the carbonyl group. So enamines share a number of characteristics with enolates. They're both nucleophiles, and if we draw this resonance structure of the enolate, we can see we get a lone pair on the alpha carbon. And so it can react like an enolate. The difference is, in an enolate, I have a full-on negative charge on my compound. And so it's a stronger nucleophile. It's more reactive, right? It's too reactive to give us the 1,4 addition that we want. In the case of the enamine, we have this lone pair, but the molecule itself doesn't have a full negative charge. Therefore, it's less reactive, and being less reactive, it will give us the 1,4 addition that we need to get a Michael reaction. And so, while the enolate can't form as a Michael donor, the enamine can. All right, so an enamine is a Michael donor. So if we react it with an alpha-beta unsaturated carbonyl compound, so if we react it with a Michael acceptor, it will act as a Michael donor. And what that will produce is both an iminium ion and an enolate. If I then react this with H3O+, I end up with 2 carbonyl compounds. So when we learned about enamines, hydrolysis of an enamine will give us a carbon-oxygen double bond. And then, of course, when I protonate the enolate, it'll give me an enol, which can then tautomerize to give me the ketone. So the reagents that I would use to get a Stork enamine synthesis, so it effectively gives me a Michael addition with a regular enolate as opposed to a doubly stabilized enolate that we used in the last video. So the steps I would take is first convert my carbonyl compound into the enamine, then react that with my alpha-beta unsaturated carbonyl compound, finally use an acid workup to convert my enolate into the ketone or aldehyde, in the imine ion, we're going to hydrolyze it to give us back the carbonyl compound. So we want to know how we would make the following compound using Stork enamine synthesis. So I have my starting material, and I want to create this product. And so if I imagine using this as the Michael donor, I would turn this into the enamine, right? This is the alpha carbon that's going to do the attacking, and so this is the alpha carbon here that's going to do the attacking. So this is the new bond that I'm forming, and so my Michael acceptor is going to be this compound, only being alpha-beta unsaturated. So what I would need to do is react this with a secondary amine. I think the textbook often uses R instead of these methyl groups, but I'm going to be specific and use the methyl group. So in this first step, I'm going to convert my carbonyl compound into the enamine. I then want to react this with the Michael acceptor that I've identified. And so this is going to be 1, 2, 3, 4, 5, 6, 7. So I have and then on the third carbon from the right, I'm going to have my carbonyl compound. It needs to be alpha-beta unsaturated. And then to convert my intermediate into the final product where they're both carbonyl groups, I need to protonate the enolate and I need to hydrolyze the imine.